everyone. Today we're starting on a new section. We'll be learning about X-rays and the Braggs. So there's both William Bragg Jr. and William Bragg Sr. there. These were two people who studied X-rays and in particular used them to look at the structure of crystals. So to start off, we'll be learning just the basics of diffraction and X-ray diffraction. Diffraction is probably a term that you've heard before in terms of light or just waves in general. We can see here a diffraction pattern caused by two waves spreading out. So, first of all, let's look at diffraction in terms of light or electromagnetic radiation. If we look at the shadow of an object, like this yellow cone over here, we can see that the shadow is basically the same shape. But the edges of the shadow aren't quite perfectly sharp. I mean, you can look at this with the shadow of anything, really. You can see that the outline, although it's obviously the same shape, the outline is a lot blurrier than the real edge of the object is. And the reason for this is because light spreads out while it's traveling. So the closer something is to the surface that the shadow is on, the sharper the shadow will be. And the further away the object is, the more blurry the shadow will get. So this spreading out of light is called diffraction. And obviously it can form interesting patterns when two beams of light are spreading out near each other. So diffraction is a phenomenon associated with waves, and it's been known to have been associated with waves for a very, very long time. So in 1803, this fellow over here, Thomas Young, showed that light behaves like a wave, and he did this by showing with proof that it was diffracting, and he did that by showing the diffraction patterns that occur. So he did this by passing light through a very small aperture. When this happens, it's very easy to see that the light is spreading out when it reaches the surface. So a pair of light sources will create a diffraction pattern, which we can see over here. So we have light source A at the top and light source B at the bottom. Constructive and destructive interference will create light and dark patterns on the surface that it's projected on. So if we look at this pattern over here, we can see that where the two different circles line up, we have these sort of lines coming out that we can see right at the edge here. And so in sections like this, there'll be constructive interference, and these patterns will seem lighter. Whereas in the middle there, there'll be destructive interference, and the patterns will be a lot darker. And so we get a sort of repeating light, dark pattern. So the pattern can be used to find the wavelength of the light sources. We can see that if B and A both had very long wavelengths, so the circles were separated by a big distance, then the black and white or dark and light pattern on the edge of the page here will be very different to if the circles are very close together like this, where obviously the light and dark pattern will have light and dark very, very close together. So one application of this is a diffraction grating. And we can see a diagram of a diffraction grating over here. So a diffraction grating can be used to produce spectra and other diffraction effects. The way that it works is that we have a number of light beams going through the grating or being reflected from the grating, and all sort of going in the same direction. So a grating consists of a large number of equidistant parallel lines sort of etched onto a surface, which means that light will be reflected from each one of those etched lines. That's why we have these sort of parallel lines coming off it. You can see that between each line, there's this little distance over here, and that sort of makes each beam different to the next one. And so this is called the path length difference. You see that it happens for every beam of light, and it's this path length difference that causes a diffraction pattern. It's what means that there are sort of two sources of different light rather than two sources of exactly identical light. So the distance between the lines is close to the wavelength of the waves that are being deflected from it. If they're too big or too small, then it's very, very hard to observe the diffraction effects. So obviously for a diffraction grating for a beam of light, you need the etchings to be sort of on the order of the wavelength of light, which is about 500 nanometers. Tiny, but doable. So, diffraction grating for light. let's go into something a little different. So in 1895, so roughly 90 years after light was proved to be a wave, this fellow here, Wilhelm Röntgen, discovered X-rays. We can see here a photograph of his wife's hand. The X-rays were determined to be electromagnetic radiation like light or radio waves, which had both been discovered by that point. And they had a much shorter wavelength than either radio or light. So if we remember from our section on radio, radio has a wavelength of about 1 meter, or about half a meter, or tens of meters. Light has a wavelength that's much shorter, on the order of about 500 nanometers. X-rays, on the other hand, are even shorter than that of light. They have a wavelength of 1 nanometer or less, which is really quite small. So optical diffraction gratings then, obviously, are going to be far too large to analyze X-rays. The spacing between the different parts of the grating is just simply too big for the diffraction effects to occur that we want. So in 1912, Max von Laue proposed that crystals could be used to diffract X-rays, which at first seems a little odd, because obviously the crystals here are much bigger than the optical diffraction grating that we saw. But it actually makes a little more sense than that, because the spacing of adjacent atoms in crystals, which is minuscule, is just right to diffract X-rays. So that means that we can, rather than carving or etching anything into these crystals, we can simply shine the X-rays on the crystals, and because they have atoms spaced at the right distance, they'll be able to create X-ray diffraction patterns. So von Laue's colleagues, Walter Frickmann and Paul Knipping, diffracted X-rays with a little crystal in an experiment like this. The crystal was of copper sulfate, as we can see here. So they fired an X-ray beam at the little crystal, which is represented by that little yellow scribble in the middle, and the diffraction pattern sort of spread out from it, like a diffraction grating, and hit the film, where they were able to record exactly where the X-rays were going. So in 1912 to 1913, Australian-born physicist William Lawrence Bragg developed Bragg's law, which was a way of describing how X-ray diffraction worked. So this is one of the Australian physicists in this part of the physics course, which is nice. So he used Bragg's law to investigate crystal structure and figure out just exactly how all the structures were made up. So, as it turns out, the atoms in a crystal are arranged in a repeating pattern. It makes sense, right? Because if you have a solid, then you would expect, for a crystal at least, for there to be some sort of repeating pattern inside, which means that you get this sort of crystalline effect. So they can be thought of as a series of repeating planes, as we can see over here. So we've got a whole bunch of atoms represented by these little white and green dots, and if we connect them, we can sort of get the layers of the crystal going down. So Bragg studied a number of different crystals with X-rays. We can see a couple of X-rays coming into this crystal here. You can see that some of the X-rays just bounce off immediately. Some of them go through and bounce off on the second layer instead. Some of them even go deeper down than that. And the interesting thing is, once they all bounce out, they're all roughly at the same spot, and so they'll be able to create diffraction patterns with each other once we reach this area. So let's take a look at this with a little bit of maths, because that'll help us figure out exactly what they're doing. So we can label the distance between the planes d, and we can label the angle that the X-rays are coming down at as theta. We can see that the wavelength is lambda. We're not using any numbers here because it means that we can sort of replace the letters with numbers whenever we want and still get the right answer. So Bragg's law states that there is constructive interference whenever this condition is true. So n here in this case is an integer, taking values of 1, 2, 3, and so on. And so what we can see is that this expression here, which is dependent on the spacing of the crystal and the angle that the X-rays come in with, is a multiple of the wavelength of the light. So bands of constructive interference can be seen when this happens. So whenever theta is the right value, whenever theta matches up with an n lambda over here, we get constructive interference, and we can detect that with films and so on. So that means that if we know theta and we know lambda, then we can determine d by varying theta. Of course, n we sort of know the value of as well because it has to take on integer values. So, as it turns out, crystals with different structures produce different diffraction patterns, which intuitively makes sense. We can see a pair of different crystal structures over here. On the left we have a body-centered cubic, and on the right we have a face-centered cubic. You can see that all of them have corner atoms because the unit cells are like cubes, but the other atoms in each unit cell are in different positions. As it turns out, there aren't just 2 different crystal structures, there are 32, which is, quite a lot. William Lawrence Bragg and his father, William Henry Bragg, which is a little confusing because they're both called William Bragg, won the 1914 Nobel Prize for their work on this. So it was a pretty big deal at that point. Using Bragg's law, they were able to figure out the crystal structure of hundreds of different sorts of crystals and sort them into the appropriate sort of structure of crystal. This is the end of the theory. I hope you enjoyed it. So we've learned about X-ray diffraction, the basics of how it works and how it was discovered, and the fact that it can be used to determine the different crystal structures of different crystals. So let's ask ourselves a few questions and see if we can find out how much we know about X-rays at this point. So question 1. Which of the following is the reason scientists use X-rays to investigate crystal structure instead of something simpler like optical light or radio waves? Alright, let's go through our options. A. X-ray photons carry more energy than visible light photons. Now let's take a bit of a think. X-ray photons have more energy, and we know that this is right because X-rays have smaller wavelengths, and that means that they have higher energy. But I'm not really sure that that would help us to investigate the crystal structure. If it's high energy, that just means it penetrates deeper instead of reflecting off. So it won't really help us investigate the structure if they just have more energy. Alright, how about B? X-rays release electrons from metallic surface more easily than light photons. Well, we can have a think about this one as well. If you go back to the photoelectric effect, we know that high energy photons, like ultraviolet or X-ray photons, can indeed release electrons more easily. But that's not really the best way to investigate crystal structure, is it? The photoelectric effect happens with metals and semiconductors. It's not really the thing that we want to be looking at if we're trying to investigate a crystal. So it's not B. Is it D? X-rays were newly discovered and the Braggs were studying their properties. That's not quite right either because Bragg first wrote down his law about 20 years after the discovery of X-rays. And so while, yes, they were experimenting, it's not really the reason they used X-rays instead of visible light. The correct answer, in fact, is that X-rays have a much shorter wavelength than visible light. So we see that C is the correct answer. And the reason for this is because the wavelength of the photons that are being diffracted have to be similar in wavelength to the distance between the spots on the diffraction grade. So for optical light, we can physically sort of carve in little lines that are about 500 nanometers apart. Whereas for X-rays, we can use the atomic spacing between atoms in a crystal. And so the reason that we can use crystals for that is because they have spacing between the atoms comparable to the wavelength of an X-ray. Question 2. Crystal diffraction of X-rays takes advantage of the wave or particle nature of X-rays, or both, or neither. Well, let's think about this. The Braggs used diffraction to investigate the crystal structure, right? So we have to ask ourselves, is diffraction a particle phenomenon or a wave phenomenon? As it turns out, the Braggs didn't need to consider X-rays as photons at all for their experiment. So B and then obviously C are both wrong. So diffraction is in fact a wave phenomenon. So we find that the correct answer is A. They took advantage of the wave nature of X-rays. Question 3. Explain why the Bragg's experiment would not have worked if visible light had been used. And this sort of relates to question 1. So the answer that I'm looking for here is something like this. The wavelength of the incident radiation must be about the same size as the spacing between atoms in the diffraction lattice. And otherwise you can't really get proper interference patterns being produced. So the wavelength of visible light is far larger than the atomic spacing in crystals, and so it can't be used to observe these diffraction patterns. Question 4. Using these constants, calculate the energy of a radio photon of wavelength 1 meter. So we're going back to radio for a bit, but we're still working with electromagnetic radiation, so it's the same sort of physics. All right, now let's see if we can remember our formula for the energy of a photon. It looks something like this. E equals hc on lambda. Sounds familiar, right? So we have values for h and c already, they're just constants, and we can use this 1 meter and we can substitute it in for lambda because of course it's the wavelength. So doing that, we end up with an equation that looks something like this, just with the 2 constants on the top and the 1 on the bottom. We can put that into a calculator to find that the energy of this photon is about 1.23 times 10 to the minus 6 electron volts. Remember, electron volts are already much smaller than joules, so this is in fact a very small amount of energy carried in the radio photon. Alright, how about part B? I bet you can guess what it's going to be. What is the energy of a light photon of wavelength 500 nanometers? It's a very similar question, but this time instead of having a 1 meter wavelength, we have a 500 nanometer wavelength. That's about the wavelength of green or yellowish light. Alright, so once again, we can use our equation for the energy of a photon, hc on lambda. We substitute in 500 nanometers for the lambda and the constants for the top once again. So we end up with something like this now. At the bottom we have 500 times 10 to the minus 9, which of course is the same as 5 times 10 to the minus 7. I've just written times 10 to the minus 9, so you realize that we're working in nanometers over here. Remember that in order to use equations like this, you have to have everything in the right units. So, put that into a calculator and you'll end up with an answer like this. 2.46 electron volts. So we can see that electron volts are very good for describing the energy of photons that we can see. Now there's one more part of this question, and you don't get any points for guessing what it is. Part C. Calculate the energy of an X-ray photon of wavelength just 0.4 nanometers. So once again, we use the equation for the energy of a photon, E equals hc on lambda. We substitute h and c again, and this time for lambda we're using 0.4 nanometers, which is a tiny number. So that ends up being 0.4 times 10 to the minus 9, which is the same, of course, as 4 times 10 to the minus 10. A very small number indeed. So small, in fact, that you might even be able to describe the spacing between atoms with a number like this. So we throw the whole expression into our calculator, and we end up with 3075 electron volts, which you can see is about 1,000 times bigger than the energy of a photon of visible light. And that, of course, is a million times bigger itself than the energy of a radio photon. So we can see right away that X-rays have a lot more energy than visible light. You know, of course, that ultraviolet light has more energy than visible light because it tends to sunburn you, whereas X-ray photons have even more energy than ultraviolet. Question 5. 2 crystals are found to have different X-ray diffraction patterns, even though the structures of both crystals have the same spacing between adjacent atoms. That seems a little suspicious, doesn't it? Why might they produce different patterns? Well, let's think of what we know about crystals first of all. We know that they're arranged in repeating patterns. All right, that's fair enough. We know that they all have a particular spacing between atoms, that these 2 crystals happen to have the same spacing. But that's not all we've learned about crystals. We've also learned that crystals have different structures. And so our answer here is that the 2 crystals must have different structures, and that's why they're producing different diffraction patterns. So the diffraction pattern of a crystal depends on both its structure and its atomic spacing. As an example, the diffraction patterns produced by a cubic crystals will always be different to those produced by hexagonal crystals. So if we have a crystal with a unit cell, for example, looking like a pyramid, a tetrahedron or something, then it will always produce a different diffraction pattern to a crystal who's shaped like a cube. Because of course the planes will be in different places and they'll have sort of different thicknesses and different concentrations, I suppose. And so we can see that the cube is going to be the simplest case, obviously. But for a tetrahedron, we'll have a different diffraction pattern, even if the lengths, or the distances between the atoms, have the same value. So, this is the end of the questions. In this section, we've learned about X-rays, their energies, how they've been used to study crystals, and some of the different features of crystal structure.